Now we are going to discuss about flood, maximum probable flood and design flood. First of all, we are going to discuss about flood. What is flood? Flood means any additional water joins into the stream or river apart from the water level flowing in the river. So that may be because of the rainfall falling on the catchment area, or maybe because of the tributaries carrying water into that river. Whatever the additional water added into that stream or river, then that maybe raises the water level from one level to another level. Up to the normal water level there is no problem, and also the water level raises up to the maximum water level, okay, that water flows safely. If the water level raises beyond that maximum water level, the water flows above the bunds, then automatically the bunds of that particular river is failed. Then that type of flows is known as flood water. And next one is the maximum probable flood. Maximum probable flood is also flood expected from most severe combination of critical meteorological and hydrological conditions. Here most severe combination, that means two heads here. One is the meteorological conditions, another one is the hydrological conditions. Meteorological conditions means, you know, already I told you, that is the temperature, wind speed and humidity. Hydrological conditions, you know, the velocity, intensity of rainfall, that characteristics of that particular catchment area. So here that both are critical combinations. Normal combinations there is no problem, that is nothing but a flood. Most probable flood means critical combination of hydrological high wind velocity, that means meteorological high wind velocity, hydrological high intensity of rainfall. The critical combination of these two gives some flood that is nothing but maximum probable flood. Really this is very large flood, but is very rarely used in the design of hydraulic structures except reservoir spillway, which that means where failures would lead to great damage and loss of life. This maximum probable flood is used where we are going to design the reservoir spillways, but not all reservoir spillways, where failure would lead to great damage and loss of life. Because if we have one reservoir, some quantity of water storing in the particular reservoir, below that having one major city, that may be constructed high quality buildings and human life staying on the downstream side of the reservoir, then that spillway should be constructed in such a way that there is no problem to the dam. Then only the safe all the people as well as the existing structures downstream side of that reservoir. At that particular cases we are going to construct by using the maximum probable flood quantity. Right here, before going to design that reservoir spillway, what is reservoir? What is reservoir spillway? So as hydraulic structures, reservoir spillway is one of the hydraulic structure, but here that spillway is constructed as a part of the dam, because this is used for the remove the excess water joining into that reservoir over the spillway, that is downstream side of the spillway. So once the spillway is having capability to flow, to relieve the water, whatever quantity of water joins into that reservoir, that relieved to the downward direction, then the dam will be safe. Otherwise, if the spillway is not capable to replace, to remove the water, whatever quantity of water coming into inside, then that problem will be arises on the downstream side structures as well as human life. So here the crust of the spillway, for example, dam is having 10 meters, 200 meters or 100 meters, depends upon the requirement. The length of the dam is 200 meters. Any one location, a part of that dam is constructed one spillway. The spillway crust should be provided in such a way that the crust of that spillway should be kept the normal level of the reservoir level. If the water rises in the reservoir, water level rises in the reservoir, the water will be raises from dead storage to normal storage. Once the water level reaches to the normal storage, and again the water the inflows into that reservoir, the water will be ranges from normal level to maximum water level. In between, the crust of the spillway is constructed in such a way that that is equal to the normal water level. Once the water level ranges above the normal water level, the water will be flows above the crust of the spillway. Then the water level will be maintained, normal water level maintained in the reservoir. In some cases, the flows are too high. The capacity of the spillway is not sufficient. Then the water level will be ranges from the normal level to the maximum water level. Okay, up to that there is no problem. Then the flood water gradually reduces automatically. The gap, the space in between the normal water level and maximum water level will be that the sheet of water will be flows above the crust of the spillway. Whereas in case of maximum probable flood, that is a huge quantity of water joins into that reservoir. At that cases, we are going to design that spillway in such a way that the capacity is just larger, just size is more than the design flood discharge. Because the capacity of the spillway is more, because the high flood means that should be more than the design flood. So the capacity of the spillway is more as compared with the design flood. So the excess water joining into the reservoir is safely removed from the crust of the spillway. Right? In these cases, only this probability, maximum probability flood is used. And then design flood. Design flood is also flood discharge adapted for the design of hydraulic structures after carefully consideration of economic and hydrological conditions. Because if the design flood is a flood which this can be increased, the cost of the structure also increases. So that before constructing the hydraulic structure, we are going to design, we are going to study carefully what is the economical, what are the hydrological conditions existing on a particular area. Okay, if that may, what it indicates that the design flood increases, the cost of the structure increases, at the same time probability of annual damage decreases, because the actual flood on a particular zone, on a particular area is only 100 TMC. But that may be increased 20% because of that structure is designed in such a way that that capacity should be resisted by 120 TMC of water. So that the damages, there is no damage because the maximum quantity of water joins into that particular area is only 100 TMC. We have constructed that dam in such a way that 120 TMC. So the cost of the structure increases, if the design flood increases, and the damages are reduces. Probability for annual damages also reduces. This is about flood, maximum probable flood and design flood. And next one, methods. What are the methods used for the estimation of design flood? Here have different methods. One, increasing the observed maximum flood by a certain percentage. But for safe side, that may be increased 10% or 20% based on the existing areas. So then the structure will be constructed like that. That is nothing but increasing observed flood. That is very simple way, increasing the available flood, then we are going to design the structure. And next one is the empirical formulas and rational method, unit hydrograph applications and frequency analysis. Unit hydrograph applications already we discussed in the last class. Right now we are going to discuss about empirical formulas. So these are also used for the determination of flood, design flood on a particular location. Here empirical formulas have different types. One is considering the catchment area. First one, considering the catchment area. Second one, apart from the catchment area, consider other parameters. That means length of the catchment, width of the catchment, intensity of the rainfall, and also that slope of the catchment. And last one is the take and recurrence time interval. So here that these empirical formulas have different types. First of all, we are going to discuss about first one, that is the formulas based on the area Q equal to C A power n. Here C is the runoff coefficient, that is depends upon the catchment area, and A is the catchment area, n is also depends on the characteristics of the catchment area. This is the standard formula of based on area. Problem, equation here there is no intensity directly, rainfall depth or rainfall intensity. Already we discussed earlier, the flood or runoff is mainly depends upon intensity of the rainfall or rainfall depth. Here there is no component directly, because these are the empirical formulas. Strictly speaking, these are not given accurate values, except where they have conducted experiment for the derivation of the empirical formula. Right, this is the standard form. A is the catchment area. Right, then hence have given one formula, Q equal to CA power 3 by 4. Here this is the Q is equal to discharge, that is equal to meter cube per second. Q is the meter cube per second discharge. C is the coefficient, there is no units, area, catchment area, that is in square kilometers, power 3 by 4. Here also not included any parameter directly, rainfall intensity or rainfall depth. But they have given this formula for the North Indian basins, but this is used Central Indian basins and also Western Ghats. But this formula have given reliable values where they have conducted the experiment only for that catchment area. This formula is given reliable values, remaining are not giving accurate values, but something is better than nothing. In such a cases we are going to use this type of formulas. Here the C value is given for North Indian basis 11.4, in case of Central Indian basis 13.9 to 19.5, whereas in case of Western Ghats 22.2 to 25.0. So this is the formula, Deccan's formula. And one more formula, Ravis, they have given one formula. They have conducted the experiment at Madras state area, catchment area. They have given one formula here, Q is equal to C A power 2 by 3. Earlier Deccan's given 3 by 4, here they have given 2 by 3, that is only the difference. Here also there is no direct component intensity of rainfall or rainfall depth. So this is strictly applicable, this is applicable only for the Madras state, but this is also widely used in the South Indian also. Because, so here also K value varies from place to place. If the K, that means C value varies from distance from the coast. If the very nearer to the coast, the C value is equal to 6.75. If 80 to 2400 kilometers from the coast, C value is equal to 8.45. In hilly area, C value is equal to 10.00. It indicates that hilly areas 10.00, C value increases automatically, Q value increases, because the hilly areas velocity of the flow is too high. Velocity increases, discharge increases. The C value increases from coast to the far away from the coast and also hilly areas. And next one, English formula. This is also only considering the catchment area. Q is equal to 124 A by root of A plus 10.4. This is also as like as Ravis and Deccan's formulas. And another formula considering apart from the area, here they have considered other factors that are Q equal to 10 into K into B into V into I into log 4.97 L square by B. Here they have introduced some other parameters apart from the area. So here B indicates the width of that catchment. This is related to B parameter. B is related to catchment area. K is the runoff coefficient considered here, and also V is equal to velocity of flow on a particular catchment given here, and I is the intensity of rainfall. This direct parameter introduced here, because this formula gives accurate values as compared with the earlier three formula. And next one is the considering the recurrence interval. Here for the maximum flood discharge equal to formula Q into 1.1 plus 2.66 A power 0.3. Here considering the catchment area, for the determination of Q maximum we should calculate the Q value. For the determination of Q value, here they have introduced recurrence interval, that is depends upon the requirement. For the determination of Q, here they have calculated Q average. Here they have considered C value as well as catchment area. And this is the another method, rational method. So here rational method is the method that is also used for the estimation of design flood on a particular catchment. This method is applicable where the intensity of rainfall duration is beyond or more than the time of concentration. Then only this formula gives accurate values. If the intensity of rainfall more than the time of concentration, then only peak discharge we are having at a particular gauge location, right? Then based on that statement, intensity of rainfall more than the time of concentration, they have given one formula, rational formula here, Q equal to CAI. Here C is the coefficient, that is depends upon the catchment area, there is no units. A is the area, this is taken as acres, and I is the intensity of rainfall. Earlier cases we have taken intensity of rainfall centimeter per hour. Here in the rational formula this is taken as inches per hour. And Q equal to discharge. Earlier we have denoted this is meter cube per second. Here this is denoted by R Q6. Right, then this formula can be, this is the given formula, standard formula, this is raw formula, this can be converted into SI units. Here this is equal to Q equal to 2.778 CAI. Here Q is the meter cube per second, A is the catchment area, square kilometers, I is equal to intensity of rainfall, centimeter per hour, C is depends on catchment, there is no units. Right, here for the estimation of, for the use of rational formula, we should know the what is the time of concentration. Once we know the time of concentration period, then only this formula can be used, because the intensity of rainfall should be more than the time of concentration, then only this formula can be applied or used for the determination of peak discharge. For that here Kripps has given one formula for the determination of time of concentration. Tc equal to 0.0195 L power 0.77 S power minus 0.385. Here S is the slope of the catchment, whatever catchment we are going to take, and L is the length of the catchment, and Tc is the time of concentration, that is in minutes. Once we know the time of concentration based on the given intensity of rainfall, then only we are going to use the rational method. Right, here the C value Q equal to 2.778 CAI. C is the catchment, depends upon that, the coefficient depends upon the catchment. Here high permeable area, so high permeable area C value is equal to 0.2. Average permeable areas, high permeable areas means sand or gravel, gravel high permeable areas, C value is equal to 0.2. Average permeable values, that means loam and similar soils, the C value is equal to 0.4, and the below average infiltration, that the C value is 0.5, that are heavy clays and soils, clays, etc. Here the value of C increases in case of infiltration value increases, so C value increases. C value increases, it represents that Q value, Q is equal to some constant CAI. C value increases, so Q value is also increases. Here C value decreases, here 0.2, Q value, discharge value also decreases, because here high impervious soils, high infiltration capacity on a particular soil, infiltration is high, discharge is less. If the infiltration is too high, this infiltration is very less, here discharge is more. Some formulas, example for the clear understanding of rational method, this is the formula. An engineer is required to design a drainage system for an airport with an area of 2.5 square kilometers for a 50 years return period. The 50 years rainfall intensity in that region is given by I equal to 35 divided by T plus 10 whole power 0.35, where I is intensity of rainfall centimeter per hour and T is time of concentration is given, that is in minutes. If the concentration time for the area is estimated as 50 minutes, T value also given. For what discharge must be designed for the system. Right, this is the given problem. They have given catchment area, that is 2.5 square kilometers, 50 years is the return period. Okay, they have given one formula for the determination of intensity of rainfall intensity. The formula for the determination of flood by using rational formula equal to Q equal to 2.778 CAI. C is not given here, but they have given in the problem design a drainage system for an airport. Airport means that is completely impervious layer. Completely impervious layer means the infiltration capacity of that particular area is almost all zero. The infiltration capacity is equal to zero. The X quantity of water falling on a particular surface directly converted into, that X quantity of water is directly converted into discharge. Here in this particular area C equal to 1. C is given in the problem itself. And another one is the CAI. A is given 2.5 square kilometers. I is not given directly. Here they have given one formula 35 T plus 10 whole form 0.3. Here T is in minutes. That value also given here 50 minutes. We are going to substitute here. Then we have the I value intensity of rainfall, that is centimeter per hour. Then by directly substitute the value 2.778, C equal to 1, A equal to given 2.5, and I equal to, by this formula we have 7.38. Finally we have the 51.28 metric cube per second, that is the design discharge by using the rational formula. One more problem here. This is also as like as earlier problem. Earlier problem, what we have observed, the catchment area C equal to 1 because that drainage is constructed at a airport location because C is equal to 1. Another problem, a small watershed consists of 1.5 square kilometers of a cultivated area. C is equal to this one. Here at a particular drainage basin, what we assumed, the entire drainage basin having same characteristics. That means the C value is applicable same for entire drainage basin. Here they have given one drainage basin having different characters, because some area having clayey soil, some area having sandy soil, and some area having completely impervious layers. Once that area of that particular surface varies, the C value also varies. Here they have given different from the earlier problem. Here area 1.5 square kilometer area, C value is equal to this one. This is the cultivated area. And 2.5 square kilometer area, C value is equal to this one. This is forest area. And 1 square kilometer area, this grass cover, C value is equal to this one. There is a fall of 22 meters in the watershed at a length of 1.8 kilometers. The intensity, frequency, duration relation given is here I equal to 80 TR power 0.2 divided by T plus 13 whole power 0.4. Here where I is in centimeter per hour, as like as earlier problem, TR is the written period is in years and T is in minutes. Estimate the peak rate of runoff for 24 years frequency. Here frequency given, frequency or written period also given. So for the determination of peak discharge, we know one formula, that is equal to Q equal to 2.778 CAI. C is not given only one value for entire area. Here different C. That means area into C value plus area into C, area into C. Here that runoff coefficient into area, runoff coefficient into area, that is C value. And area they have given sum of this one 2.5. Here 1.5 into C 0.20 plus 2.5 into 0.10 plus 1.0 into 0.35, that is the area into C we have directly. Then only one parameter I equal to, this is the formula, TR they have given, written period or recurrence interval equal to 25 years. So T is not given. Earlier problem they have given time of concentration equal to 50 minutes, but here they have not given. We are going to first calculate the T value, then the T, time of concentration, then substitute in this equation, then we are having the intensity of rainfall. Then for the determination of T value, time of concentration, we have one formula 0.0195 L for 0.77, S for this one. S means that is the slope. Here they have given fall 25 meters, that depth at one location, another location is 0. The length of this one is equal to 1.8. That means the slope equal to 22 divided by 18. This is converted into meters. 22 divided by 1800. This is the S. That is length of that catchment is given 1.8 meters. Once we know the T value, that is the time of concentration 34 minutes, that is substituted calculated here, then we have the intensity of the rainfall. Once we know the intensity of rainfall, Q is equal to 2.778, A equal to, we know this is the A value, 1.5 into this one, 2.5 into this plus this one, this is the A value. Here the intensity of rainfall is equal to 25.9 by using this formula. Then finally discharge equal to 64.78 meter cube per second. One more problem. Here, this is also what we learned in the earlier problem. We have calculated the time of concentration. They have not given time of concentration T, and also they have given in the one catchment they have different layers, 3 types of C values. That is learned from the earlier problem. Here, this is another problem. A culvert is proposed area. A stream drainage an area of 185 hectares. Here they have given area that is in hectares that you should convert into square kilometers. The catchment has a slope given directly. Earlier they have given 20 kilometers level and 1.8 kilometers length. But here they have given directly slope, and the length of the travel for the watershed, this length of the L also given, length of the watershed, estimate the 25 years flood if the rainfall is given. Here also rainfall formula, that is equal to 1000 TR power 0.2 T plus 20 0.7. Here T is not given directly. So that we are going to first estimate by using the formula, time of concentration formula. This is the here they have given S directly 0.04, and length of the catchment also given. Then we have the value TC. Once this value substitute here, then we are having the intensity of rainfall 11.205 centimeter per hour. Then this value, we know the standard formula, Q is equal to 2.778 CAI. C is given here, this runoff coefficient is equal to 0.35, C given, and also area given, that is hectares. First that converts into square kilometers, and intensity of rainfall calculated here. So substitute here these values. Finally we had 20.12 meter cube per second. Here these are the problems related to the rational method.